Okay, so let's start. Robert will talk about wonders in AC0.
All right, thanks. Yeah, thanks everyone for coming. So today I'm going to be talking about a new algorithm to compute the greatest common divisors of polynomials. This is something we've all seen before. We all know how to compute these. But what will be interesting about this is, as Avi said, it'll be an AC0 type algorithm. It'll be a constant depth algorithm, which in particular means that you can execute it very quickly in parallel. So before I actually tell you anything about this algorithm, let's just spend some time reminding ourselves, what are greatest common divisors, and what do we know about computing them so far? So we have two polynomials, f and g. Their coefficients come from some field f, and their greatest common divisor you can define this a little bit abstractly. For me, I just want to give a very usable definition, which is this is any common divisor of maximum degree. And you can also define greatest common divisor of integers and more abstract objects, but here I just want to talk about polynomials. So as an example, just to warm up, it's still early in the morning, maybe your caffeine hasn't hit you yet. So if I have two polynomials, say, this is f, this is g. So I have f, which factors as this, g, which factors as this. What is their GCD? Well, what you do is you take each factor and you take the largest multiplicity that divides both polynomials. So here, this is x minus 1 times x minus 2. Here I'm implicitly using some facts that polynomials have unique factorization. Let's not worry too much about that. So this is the GCD, and what's interesting about this is you can compute this. And we all remember in kindergarten, we learned the Euclidean algorithm. We know how to compute these efficiently. So let me remind you what the Euclidean algorithm looks like, because this is going to be our baseline that we try to improve on.
You can compute it without the factor.
Yeah, exactly. So one way you could compute this is you could be extremely clever and try to factor f and g, and then just compute the GCD by taking each factor with the minimum multiplicity that you see. But you can compute this without actually knowing the factorization of f and g. And the way that this was first discovered was via the Euclidean algorithm. So let me just remind you what this is, because this is going to be our baseline. So it's an iterative algorithm. We start out with f and g. And then what we're going to do is, what we're going to do is we're going to take f and g, and in the first step we take f, divide it by g, and replace f with its remainder when you divide by g. And then we're going to do this again. We're going to take g, divide it by whatever that remainder was, and continue until we see 0. So in each step of the algorithm, I'm going to write down the remainder of ri minus 1 when you divide it by ri, and then pi. And then at the very end, ri is 0, so whatever the last non-zero remainder we saw was, that's the GCD. This is a very simple algorithm. If you want to, look at the running time of this, this is going to take you some polynomial number of arithmetic operations. Polynomial in the degree of f and the degree of g. This algorithm also works for integers. It's some polynomial time algorithm. And you could consider two different, ways of improving this. One is, can you get a faster algorithm? So it turns out you can actually do much faster. So This was first observed, I think, by Knuth, then improved by Schoenhager. Both are doing this for integers, and then subsequent work by Monk extended this to polynomials. But you can actually find a fast variant of the Euclidean algorithm. You can compute the GCD in something like order n log squared n arithmetic operations, where here n, this is just the maximum of the degrees of f and g. This is a really interesting algorithm. The observation is that, while your remainder is above degree, say, n over 2, the steps of the algorithm really only depend on the top n over 2 coefficients of f and g. So you can really do some kind of divide and conquer strategy where you run the Euclidean algorithm only on the top halves of f and g. You get some results. You have to clean it up a bit to incorporate the lower order coefficients, and then you recurse on the lower order coefficients. So this gives you a much faster algorithm, but both of these algorithms are sequential. Right? And it seems like they're inherently sequential, at least the way that they've been written down. So the question that I want to explore in this talk is, can we do this in parallel? And I should mention that, for integers, it's conjectured that you probably can't get a fast parallel algorithm. But for polynomials, the answer turns out to be yes. And the way we're going to get a parallel algorithm for polynomials is we can rephrase the question of computing the GCD in terms of linear algebra, which is something we don't have access to over the integers. So now I want to tell you some amazing fact that allows you to start incorporating linear algebra into your GCD computations. So let's say I have two polynomials. And throughout this talk, whenever I have polynomials as input to a computational problem, they're given by their coefficients. But I might write down the polynomial as its factorization, but always the input is the coefficients. So I have two polynomials, f and g, and for simplicity, let's suppose they have the same degree. So here's a fact that you learn, maybe not in kindergarten, maybe this is like second grade. So the GCD of f and g is 1 if and only if a certain nice thing happens. So what is this nice thing? There exist polynomials a and b such that the following things happen. So one is that a and b should be fairly low degree as polynomials. So they'll both have degree at most n minus 1. So a and b have somewhat low degree. And then the third condition is that if you look at the polynomial af plus bg, this should be equal to 1 as a polynomial. And what's interesting about this is, if you look at these are really linear equations. In the coefficients of a and b. Right? I know there are at most n coefficients of a and n coefficients of b. And so I can really write down, for every monomial in this polynomial, I can write down an equation that says the coefficient of that monomial is either 0 or 1, depending on its degree. And yeah, you can write this down explicitly, and I'm going to, because we'll see this matrix later on. This is roughly 5. Right. So you're really trying to see if this is the linear system of equations. Here the unknowns are the coefficients of A and B. You know the coefficients of F and the coefficients of G. And here both of these parallelograms are with n. So this is a 2n by 2n square matrix. And you want to solve this system. Now I should mention that this is only to check if your polynomials are coprime. But there are similar sets of linear equations that characterize when the GCD has degree d. So you can actually, look at all of these sets of equations in parallel and do something with this. I'll talk about parallel linear algebra in a minute, but I just want to say, before we leave the GCD behind for a little while, that this was used in a work by Borden, von Zagatten, and Hopcroft in 82 to compute, right? So they compute the GCD in using this and similar ideas. They compute the GCD in log squared n parallel time with a polynomial number of processors. And what's going on here is, as we'll see in a minute, we can solve all our favorite linear algebra problems quickly in parallel. So by having this linear algebraic characterization of the GCD, we actually unlock a lot of tools that we can use for parallel computation. And this, you could argue, is maybe why we have parallel algorithms for polynomials, while the integer case, well, we don't. We think it's sequential. Okay. So now I want to leave the GCD behind for just a little while. And I want to talk about parallel algebraic computation. I want to see, what can we do in parallel? How do we do some of these linear algebraic operations in parallel, and how are we going to improve? Yes.
Before we continue, can you sketch it all how you get the GCD instead of just checking coprime?
Yeah, okay. So how would you get the GCD? So the right way to fix this is the condition you're checking is if the GCD has degree d. And here you're going to ask that the degree of A should be something like at most n minus d minus 1. Same thing for the degree of B. And then you want to say that AF plus BG equals the GCD. And so the linear equations you get out of this are you say that, well, the degree D coefficient here should be 1, and everything above that should be 0.
Sure.
So you end up taking something like a submatrix of this. Yeah. Okay, great.
Oh, wait, sorry, but that's the degree of the GCD. What about like the actual coefficients?
Right. So first, let's say, how do you even find the degree? I can look at all these systems of equations in parallel and check which ones have solutions, which ones don't.
Sure.
Okay, now find the one with the minimum degree, solve it, find A and B. And now you know that AF plus BG is actually the GCD.
When you set up the system of equations, how do you write down the GCD on the right-hand side if that's what you're trying to find in the first?
Right. So I don't write down the GCD on the right-hand side. I say that this linear this combination here, AF plus BG, it should have exactly degree D, and it should have leading coefficient 1. So I say that the degree D coefficient is 1, And I say that everything above that is 0, but I put no constraints on the lower order coefficients.
Again, that implies that I see, because that implies that it's a divisor, and
Right, it's a divisor, it's the right degree, so it might as well be the GCD.
I see, okay.
Yeah. Any other questions? Okay. So before I tell you about parallel linear algebra, I want to make precise what I mean by parallel. So really, the model of computation I have in mind uses algebraic circuits. So if you haven't seen these before, I just want to tell you what these are and tell you a few complexity classes that we're going to look at in this talk. So algebraic circuits, these are a circuit model for computing polynomials. So what are the gates you get? Well, the inputs are some variables. The gates are addition gates. You also have multiplication gates. And finally, on the wires, maybe you can put some constants. So maybe I'll put a -1 here. So what does this circuit compute? Well, this gate computes x plus y. This one computes x minus y, and then their product, the output, is x squared minus y squared. So this model is arithmetic computation. And there are two parameters that we'll care about. One is the size of a circuit, which is just the number of gates. And the second that I care about is the depth. And the depth here is going to be the length of the longest input to output path. So for example, in this circuit, well, it has size 3 because I have 1, 2, 3 gates, and it has depth 2, right? There are, every input I can reach the output in a path of length 2, and there's nothing more. And in particular, we're going to care about depth because this is some measure of parallel time, right? If I have a very shallow circuit, I can layer by layer evaluate the gates in the circuit, and this will yield a parallel algorithm. So I want some shorthand, so you'll have to forgive me for this, but I want to tell you about 3 complexity classes that we'll care about. So they'll be defined in terms of restrictions on the size of the circuit that we look at, the depth, and then finally the fan-in of the gates. So here in the circuit I drew, every gate just takes 2 inputs, but you could consider circuits that have much wider fan-in. Maybe they have more inputs. Okay. So the first class I want to consider is what I'll call AC0. So this corresponds to circuits, polynomial size, constant depth, and unbounded fan-in. So I haven't told you what n is in this circuit up here, but certainly this is constant depth at step 2. So these are sort of if you want to think of this in terms of parallel time, these are sort of the fastest parallel algorithms you could hope to write down. They're constant parallel time, but of course, if you want to actually run this on a computer, you can't add n numbers in a constant amount of physical real world time. But anyways, the next class is this NC1, which again is polynomial size, but now I give you more depth. I give you log n depth, but I force you to have gates of fan-in 2. And you'll see that AC0, this is contained in NC1. And why is this? Well, every time I have a gate of very large fan-in, I just replace it with a binary tree with fan-in 2. And this might incur a logarithmic factor in depth, but that's fine. Then the last class that I'll care about is NC2. Again, we have polynomial sized circuits, but now I give you an extra log factor in depth. So log squared depth, but again, fanning. And we'll see that a lot of algorithms that we know will fall into this NC2 class, so polynomial size log squared depth. And the new work that I'm going to tell you about today fits more here, this AC0, polynomial size and constant depth. So, and one more thing I should mention is that NC1 captures what are called formulas, in the sense that here I was allowed to reuse some gates. Maybe this example is not so good. You could imagine that, you have some intermediate gate in your circuit and you want to reuse the result many times. This is perfectly legal in circuits, but in what's called a formula, the graph of this circuit is a tree, in the sense that if I want to reuse some intermediate result, I really need to recompute it again. And it's, it takes a proof, but in fact, formulas, they correspond exactly to what's computable in NC. Okay. Young, did you have a question? Oh, okay. Okay. So now let's leave the GCD behind and talk about linear algebra. Okay, so I claim that we can do a lot of interesting things in linear algebra in this NC2, this log squared depth. But how would we actually do that, right? If you think about this, if I want to invert a matrix, well, it's not so clear how would you do this in parallel? How would you even compute the determinant in parallel? That part's not even so clear. So let's start with something extremely basic, just to, sanity check ourselves. So the first problem that you might consider if you're trying to build a package for parallel linear algebra is what's called iterated matrix multiplication. Where here, you're given matrices, say A1 through AN. These are n by n matrices over your field. And you want to compute their product. You just want to multiply these matrices. So how would you do this? Well, of course, you can do this in polynomial time. How would you do this in parallel? Well, the answer is easy. You would just write this matrix product as a balanced binary tree of matrix products. This tree of matrix products has log n depth. And each individual matrix product will cost me log n depth to implement. So, our sanity check is good. We can at least do this iterated matrix product in this class NC2, polynomial size log squared. We can do that. What about the determinant? Can we compute the determinant in parallel? Can we even compute the determinant using an algebraic circuit? Well, how would you compute the determinant normally? You could try Gaussian elimination. This certainly computes the determinant, but this seems like a sequential process, right? Every time you perform a row operation, the next, whatever you do in one step determines what you do in the next. Right? This is a sequential process. And you're also using divisions. So let me just mention, there's a sort of keystone paper of Strawson in this area that says divisions are actually unnecessary. But you can take Gaussian elimination and in some way remove the divisions from the algorithm and actually get one of these algebraic circuits. And the way you do this is anytime you divide by a polynomial, you're really going to simulate this by inverting that polynomial as a power series, and then you do some cleanup. Let's not worry about that. This is a sequential algorithm, so how can we do that? I want to remind you of this notion of the characteristic polynomial. This is some polynomial in a variable t. The leading term is, plus or minus t to the n, depending on the parity of n. And then constant term is the determinant. So certainly if I can compute the characteristic polynomial, I can compute the determinant. So now here's an interesting identity that goes back to work of Samuelson from the 40s. And then this was used to describe an algorithm by Berkovitz in 4. So here's an idea that you can use to compute the characteristic polynomial. Say you have a matrix A, you want to compute its characteristic polynomial. Let's take A, and I'm going to break it into a block matrix. So I have a 1 by 1 block in the top left corner. I have a 1 by n minus 1 block, which is some row. I have a n minus 1 by 1 block, some column. And then there's some large matrix, say B, in the lower right-hand corner. Now, what's amazing about this is, okay, so one piece of notation. So I'm going to use AI, the coefficients of A's characteristic polynomial. And I want to use BI's for the coefficients of B's characteristic polynomial. And what they showed is that there exists some matrix, say Mn, such that if you want to compute the coefficients of A's characteristic polynomial, well, you can take the coefficients of B's characteristic polynomial and multiply them by this matrix M. Right? So there's some, if you can compute the coefficients of B's characteristic polynomial, and you can compute this matrix somehow, you get the characteristic polynomial of A.
The matrix Mn, is it like fixed for all matrices A, or?
No, so it will depend on A.
Okay.
But the key point is, if I give you A, you can compute this in parallel. There's some explicit expression for it in terms of, powers of A, R, C, and A. You can compute it very quickly.
Okay.
And there's some explicit formula I didn't want to write down here. But the point is, where do I want to go? Well, finish this thought here. The point is, now you can recurse. You can write the characteristic polynomial of A as an iterated matrix product, where every one of these matrices you can compute quickly in parallel, at which point you compute the product in parallel. So this tells us that we can also compute the determinant in the same class NC2, log squared depth polynomial sense. Okay, so that's great. We're seeing more and more. So what else can we do? Well, we also needed to invert matrices so that we can solve systems of equations. So how can we do that? Oh, there's actually a very simple way we can reduce the inverse to what we've seen already. All right, so for inverse, we're given A. we want to compute A. So keeping the notation for the characteristic polynomial, we're just going to use everyone's favorite theorem from linear algebra, the Cayley-Hamilton theorem, which says that A satisfies its own characteristic polynomial. So now why is this interesting? Well, let me expand this out. What's the constant term here? Well, if I take the constant term and move it to the other side, it's minus the determinant of A times the identity matrix. And what's on the other side? Now I have I at least 1, AI times A to the I. And I can factor out a power of A here. And you'll notice now I have two matrices which are multiplied here. I have A, and I have this linear combination of powers of A, right? I can compute these little AIs in parallel. I can compute these powers in parallel. And you notice that this product, well, up to this scaling here, is the identity matrix. So this matrix here is the inverse of A, up to scaling. Right? And it's scaling by a factor that we can easily compute. Okay. So all this is to say that you can also compute the inverse. So we can basically, you can do this for any other linear algebraic problem you like. You can essentially do all of linear algebra in AC2. Can you do better? What do you think? Can you do better?
Sharp L, gap L.
Gap L, sure, okay. Yes, you can be a little tighter and say that, there's something even below this that is really what's going on. I only want to use these alphabet soup. So can we do NC1?
Not in general.
Not in general, no.
Except,
We don't know.
on collapses.
Yeah. So in general, we don't know. Let me tell you one thing we do know, which is surprisingly recent. So there was this wonderful work by Limaya, Srinivasan, and Tabana from 2021. In fact, I remember the day that this paper was posted to ECCC, I woke up, it was 6:30 in the morning, I saw the title, and I was completely dumbfounded. I thought, this can't be true. What just happened? The world changed, and they showed that the determinant actually cannot be computed in AC0. There's no polynomial-sized constant depth circuit that computes the determinant. And, well, we don't know. Is the determinant actually in NC1? The conjecture is that this shouldn't be true. There should not be a polynomial-sized formula, but we don't know how to prove that yet. So all this is to say that linear algebra, this is a wonderful tool for designing parallel algorithms, but it stops at this NC2. You certainly can't go to AC0, probably not even NC. So if we're going to go below this, we need to find some other ideas. Yeah.
When you say AC0 here, it's like algebraic AC0.
Yeah. So, okay, good point. So I wanted to hide all of that under the rug. All of this is some algebraic set of complexity classes. You could also define this in terms of Boolean circuits, which is probably what people really mean when they say something like AC0. But
I guess it's just for Boolean AC0, it's trivial because determinant handles parity and things like that.
Yes. So yeah, and that's a funny point about this, that we've had lower bounds for AC0 for decades. And this algebraic AC0, we only have lower bounds from a few years ago. Up until this, maybe the best lower bound was like a cubic lower bound, and that was from the mid-2010s. So, and I think before that, maybe it was quadratic from 2001, something like this. Yeah, it's
It was really strange because the algebraic world is supposed to be more structured, so you should have an easier time proving lower bound. And this was, it was amazing. With hindsight, given the techniques, they could have been discovered earlier, but
any words on how the proof looks like? If the answer is like, go read what's going on, that's completely fine.
No, you don't have to go read. I mean, but if you don't know anything, you have to read something.
Okay, sure.
There are techniques that has to do with using the structure of the polynomial you compute, in particular, the space of partial derivatives of this polynomial to enable you to prove lower bound if it's rich enough. And we knew how to use it, but not to get this kind of result. We knew it mainly for homogeneous circuits. And they, managed to take this tool and really, go deep into it and use it in an ingenious way, I would say. Because I was definitely trying to do this for some years. And managed to restore in terms of techniques were there 30 years earlier, but there's a combinatorial, development of these techniques that elaborated there that's really absolutely beautiful.
Yeah. So maybe I don't want to say too much about it here, but I'd be happy to talk later about this. I should mention that there's been quite a lot of work extending this and proving more lower bounds and sort of pushing the technology since then. So there are more papers on this, some by a superset of this set of authors, or exactly this set of authors may be permuted. It's really been an active area of work in the past few years. Okay, so all this is to say we have these fast parallel algorithms, but we want to do better. And why can we even hope to do better? I don't have that system of equations, but you saw that the equations we use to characterize the GCD, they're very structured. They're not general linear equations. There's some extra structure going on, so we could hope to do better. So, okay. So what can we even hope to do in parallel, right? I'm really shooting for AC0. So what kinds of tools and techniques do we have? So the first thing I want to tell you about are these polynomials called the elementary symmetric polynomials. And these are going to be one of the stars of the show today. So it's worth spending some time on them. So this is going to be a polynomial of degree D, and its name is E for elementary symmetric. N-variate polynomial, and what is it? Well, you're going to sum over all subsets of the variables of size D, and you're going to take the product over all variables in that subset. Right, so this is multilinear, it's symmetric. If I permute the variables, the polynomial doesn't change.
So the analog of the Boolean threshold function.
Yeah. Something like a threshold or a majority, maybe. Okay. So what do you think? I'm kind of spoiling the surprise. But do you think you can compute this in parallel? Can you design a formula that computes this? What do you think? Yeah, so you can design a formula. In fact, you can get constant depth. So let's see how you might compute something, it's kind of surprising that you can compute these in constant depth, because this polynomial has something like n choose d terms. How would you collect all of those in a nice structured way? So this is really an observation that goes back to Banor from the 90s, that you can actually compute these polynomials in AC0.
Early 80s.
Early 80s, okay. Sorry. I see. Yeah. Okay. And I should mention, just as a bit of notation, sometimes I'm going to abbreviate, a collection of variables just by putting an overline. So this is, okay, how would you compute this in constant depth? Well, this is a constant depth expression, right? It's a sum of products, but it's exponential size. So we have to do better. And the idea is really to use polynomial interpolation. So I want to show you the proof, because this is a really powerful idea. So I want to look at this polynomial. So y here is a new variable. Now this I can certainly compute in constant depth in polynomial sense, right? I've written the circuit here. Now, as a polynomial in y, well, what is this? Well, the coefficient of y to the I is exactly the ith symmetric polynomial in the x's. Right? If I want to get y to the I need to pick the x variables I different times. I get all of the I different ways to get them. So now, use the simple fact that you can interpolate a polynomial's coefficients from evaluations of the polynomial. So what does polynomial interpolation say? There are some constants, so Cij, such that EI, this ith elementary symmetric polynomial, is, to get this right. So I'm going to take a linear combination of valuations of this polynomial at different points. So if you think of this as a polynomial in y, I can evaluate it at some point for y, say, 1, 2, 3. And if I take n plus 1 evaluations of this polynomial, then from those evaluations, I can take some linear combination and recover the coefficients. Right? So this actually gives you a depth 3 circuit to compute these elementary symmetric polynomials. And it's a quadratic size circuit. I mean, this is a fantastic result.
Robert?
Yes.
Stupid question.
No stupid
What happens
question.
if the field is small?
I need a large field for this.
Okay.
Yes. So I didn't want to say it, but later on we'll see that I need a large field. I actually need large characteristic as well. So
think about the real.
think about the complex numbers.
Okay.
Because those are nicer.
Okay.
But yeah.
But you can think about if P is bigger than n or n squared, that's also good.
Yeah.
Okay.
Yeah.
I want to remark that if you take a really small field like F2, then you are back to Boolean computation. And then you cannot do this thing. Right? So really constant size fields are like the Boolean setting and you don't get parallel anything.
Yeah. Okay. So, this is a nice algorithm and we can compute something in constant depth, but why should you care about these polynomials? So one reason that you might care about these is the elementary symmetric polynomials actually correspond to coefficients of univariate polynomials. So say I have some univariate polynomial, which, we all remember over the complex numbers, a univariate will factor into linear terms. So if you write this as a polynomial in X, what are the coefficients? The coefficient of x to the n minus I is the ith elementary symmetric function of the roots. So the point here is up to this sign. Forget the sign for a second. What are the coefficients of this polynomial? The elementary symmetric functions of the roots. So that's one reason to care about these is somehow these are connected to roots of polynomials, from their coefficients, which we'll need later on for the GCD. And the second reason you might care is that these polynomials, as the name suggests, they play a key role in the theory of symmetric polynomials. So I just want to briefly digress. So what are symmetric polynomials? Oh, these are polynomials that are unchanged under permutations of the variables. So I say f is symmetric if for all permutations pi, f variables in the standard order is the same as f with the variables permuted by 5. So these are very nice polynomials. They have some structure. And there's a theorem, which is sometimes called the fundamental theorem of symmetric polynomials. And what does it say? It says that for every symmetric polynomial f, there exists some polynomial g in n variables such that what? Well, if you write f, you can actually express f in terms of the elementary symmetric polynomials. So if you take g and evaluate it at these elementary symmetric polynomials, you get back. So you can always do this. If a polynomial is symmetric, you can explain it using the elementary symmetrics.
Of degree n.
No, for any degree.
Oh, sorry, you can have arbitrary.
Yeah, so G could have degree, right? I could take products of these elementary symmetrics, And it turns out that this G is essentially unique. So these elementary symmetrics are some analog of a basis for the symmetric polynomials. They're really, they're nice, they're important. And we're going to talk about them all. Okay. So this suggests that maybe there are some other things we can do with symmetric polynomials in low depth. So let's see, what else can we do? So another family of polynomials that's very interesting are what are called the power sum polynomials. And these will also hang out a lot during the rest of the talk, so it's good to meet them. So this is some degree d polynomial, and it's just, you take the variables, and you take the sum of their dth powers. Right now, clearly this is computable in constant depth. These things are very easy, very, nice. Why are the power sum polynomials interesting? Well, they're clearly symmetric. And in fact, this same theorem holds if I use the power sum polynomials instead of the elementary symmetric polynomials. They also generate all the symmetric polynomials. Although that's over fields of large characteristics. Small characteristic, there might be some issues.
How many of them do you need? And
Yeah, you need up to n. Right. So that's a good point. The elementary symmetrics, they only go up to degree n. These appear in all degrees. But to generate the symmetric polynomials, you only need up to degree n. Okay. So, in fact, this theorem that says you can generate any symmetric polynomial using one of these two families suggests that you should be able to convert between them. Right? If I give you the elementary symmetrics, you should be able to write the power sums and the other way around. So how do you do this? So there's a collection of identities, which are known as Newton's identities. And these give you some explicit conversion between these families of polynomials. This gives you some way to map between the first n power sum polynomials and the elementary symmetric polynomials. And in fact, these identities are not too hard to write down. So I'm going to write them down the way you would see them when you search for this on Wikipedia. So what do they look like? Well, you have some identity like this, that if you take the dth power sum plus or minus d times the dth elementary symmetric polynomial, and you can determine these signs, but don't worry about them. You can write this as some inner product between the elementary symmetrics and the power sums. And why is this useful? Say you know all the elementary symmetric polynomials, and you want to compute the power sums. So what do you know? You know ED. you know all the e's that are appearing here. And by induction, you have all the p's that you need to fill out this expression. So you can solve for the dth power sum and keep going. So this gives you some sequential algorithm to perform this conversion, but we need parallel. So there are other ways of expressing these identities. Let me tell you one of them. So here I want to I'm going to look at some formal power series. So here x is just the formal power series corresponding to the exponential function. And it turns out that you have an identity of power series. So on the left, I have the elementary symmetrics, or the coefficients of this power series in Y. And on the right, well, I have something a little bit more complicated. So let's do this. So there's some, power series, infinite power series in Y, whose coefficients are the power sums. You take its exponential, and you get back the elementary symmetric. Okay, now this is an identity, but it doesn't seem that useful. Because here you have something like an infinite degree polynomial. And what I'd really like to do is use some kind of, interpolation, like we did here, to recover the elementary symmetric polynomials. How could we do this? Well, the way we're going to do this is we're just going to truncate this identity and show that the truncated identity actually works. So I need one thing, which is, let's look at the truncation of the exponential up to the nth power. And you can show that if you take the truncated exponential of, this same series, but also truncated to degree n, this gives you the power sums plus some junk terms, but these junk terms are of higher degree in Y. That you've expressed this identity up to precision n, so you should expect to get the right answer up to precision n on the right-hand side. So the point is, now if you use interpolation, you can compute the EIs from power sums in constant depth, right? This is going to be some expression that you can write down in constant depth if you're given the power sums. And then you do this interpolation trick that adds one more layer onto your circuit. Okay, so this is one thing we can do in constant depth, is convert from the power sums to the elementary symmetrics. And you can go the other way. How do you do that? Well, if you kind of squint at this and write log on both sides, you can make it work out. Right? On the right-hand side, you have something in terms of the power sums. On the left-hand side, you have something in terms of the elementary symmetrics. So the point is, in constant depth, we can convert between these two families of polynomials. And it turns out that this is actually going to be very, very useful for us for computing the GCD. So maybe I'll just pause here. Any questions on this? Okay. All right. So now that we have this, I want to actually give you an application. This seems like we're just building a lot of theory, and I promised you an algorithm to compute the GCD. I won't make good on the promise yet, but let me show you something this lets you do that's already suggested that we're doing something interesting. So here's one new algorithm that we can write down. The result isn't new, but it's a cool algorithm, I think. So what's our input? Our input is two polynomials, f and g, with complex coefficients. I'm just now specializing to the complex numbers because I want a large field. I want large characteristic. Maybe I should say the large characteristic comes from the fact that I want to make sense of 1 over I. Right? I want to divide by 1, 2, 3, 4, 5. I can't do that in small characteristic. Okay, so given this input, this is a promise problem. So the promise is that G divides F. We can compute the quotient F over G in AC0. And already this feels like maybe we're doing something new. How do you prove this? So let's write down the factorizations of f and g. Right? We don't know the factorizations, but this will help us analyze the algorithm. So say f has some factors x minus alpha I and some additional factors f minus beta I, and g divides f, so it shares this set of factors x minus alpha I.
It was not obvious it is in NC too. I mean, it's not completely obvious that the program is big. I mean, it was also realized in the 80s, but
Right. So you can, again, use linear algebra. You can do something even more clever, more specialized. But yeah, it's not even clear that you can do this in parallel. Okay, so what's our algorithm here? Okay. First step is I'm going to, from f and g, I'm going to convert them to their power sums. Right? I told you that the coefficients of f are the elementary symmetrics in alpha and beta. And the coefficients of g are the elementary symmetrics in alpha. So I can convert to power sums.
Can I ask something before you go into an algorithm?
Yeah.
Why doesn't the following work? I just evaluate f over g on like some points and interpolate.
Yeah, that also works. Yeah. Interpolation is fine, but this will give you an idea of maybe how to use these power sums in an interesting way.
That's good.
Yeah. Okay. So what I want to do is I want to compute the power sums of f, which are in the alphas and betas. And then I also want the power sums from g, which are the power sums in the alphas. And now we're going to subtract. Right? So how do you get the power sum in just the betas? Well, this is power sums in alpha and beta minus the power sums just in alpha, right? Okay, so now I have the power sums in betas. And now I just compute the elementary symmetric polynomials in beta using Newton. Each one of these steps is in constant depth. And I have a constant number of steps with a constant depth algorithm. And what's interesting here is, in some sense, we're using these power sums as like a logarithm, right? We're converting division into subtraction. So even though it's not exactly a logarithm, it's filling the role that a logarithm would play. So this is giving us something interesting. Now I should remark that there's a results of Bini and Pan from, I think this is from 85, they show that division of polynomials, even with remainder, is in AC0. And this is using some more clever specialized linear algebra. You don't need the promise that G divides F, you can get the remainder. The algorithm I'm sketching here only does exact division, right, when G divides F. But we can also handle division with remainder using things I'm not going to tell you about today. So they're different algorithms, it's the same result, but somehow this is a different perspective on it.
Robert?
Yeah.
You're using the fact here that the characteristic is large, but you're not using the fact that C is closed, right? I mean, you can always.
The only thing I'm using about C is to justify, I'm going to write polynomials as linear factors.
Yeah.
And this is all for analysis.
But this is like only for the analysis, you don't need this closed.
Yeah,
Exactly,
you can
exactly.
work over any field. You imagine the algebraic closure factorized completely, and you never need it.
Okay.
Yeah, so if your input has rational coefficients, you'll never leave the rationals. But the analysis, I need the closure. Yeah. Okay. All right. So now we've done all this work to talk about these symmetric polynomials and these conversions. Now we can really start talking about some fun algorithms. So now we're going to make progress towards the GCD. Okay. So here's the first, I think, really first thing to maybe change your perspective on this problem, something new that we didn't know how to do before. So let's say I'm given two polynomials, f and g, where f factors into this set of factors x minus alpha I. We can compute the following thing in AC0. We can compute the sum of g evaluated at alpha I. So I'm going to take g and sum it over the roots of f. And I'm going to do this without actually factoring f. I'm going to do something else. Before I prove this, does anyone see how to do this? No. It's a two-line proof. And the only trick is to change the order of summation. So let's expand this in terms of the terms of g. So here, what is this? Well, I have the jth coefficient of g times alpha I raised to the power j. Change the order of summation. I have gj. And now if I collect like terms, what do I have? Well, I have alpha 1 to the j summed through alpha n to the j. How do you compute this in constant depth? Convert to the power sums for f and take this integral. That's it. I should say one thing that is being used here that may not be clear from the high level view is g might have larger degree than f. So I might need to go to very high degree in the power sums, but this identity I showed you earlier allows us to do. All right, so what else can we do? This is nice, we can sum over roots, but maybe I want to compute some more interesting function over the roots of that. And what else could I do? And here's another result. So again, we're given f and g, where f has roots alpha I. We can compute now any elementary symmetric function of g evaluated at the roots of f in AC0. So this lets us do even. How do we do this? We're going to use the Newton identities again and some interpolation. What do we do? So if I first want to interpolate the coefficients of g to the k. All right, really what I want to do is, instead of computing this elementary symmetric function directly, I'll compute power sums of these g at alphas, and then use Newton's identities to get the elementary symmetric function. So now here, what we're going to do is, now that we have the coefficients of g to the k, we can compute the kth power sum of g evaluated at the alphas. And now we can get the elementary symmetric function using Newton's identities again. Okay, so now we can actually do quite a lot with this. If we have two polynomials, we can evaluate one over the roots of the other. Now, why would you even think of doing this? Well, let me go back to the GCD. Yeah.
Why can you interpolate in constant depth the coefficients of the?
So here, how would I compute g? I have here g0, I have g1 times x, g m times x to the m, right? So I can certainly evaluate g at any point I like. And now I feed this into a product gate with very high fan-in, right? Fan-in k. So now
Right, you can like, it's not that you only have unbounded fan-in, you can also fan-in something. Okay.
Yeah, so this computes g to the k, and now I interpolate using this circuit. Is that clear?
Yeah.
Okay, great. Okay, so now I want to go back to the GCD. And I showed you this interesting set of linear equations earlier, so we're going to come back to this. So the fact that I don't want to prove here that the GCD of two polynomials is 1, exactly when the determinant of this matrix I drew at the beginning of the talk this matrix should be invertible. Right? This characterizes exactly when f and g are co-prime. And this determinant, it has a name. This thing is sometimes called the resultant of f and g. This is just saying the resultant is non-zero exactly when f and g are co-prime. Now, how would you compute this thing? Well, it's clear that if you just invoke any algorithm you like for the determinant, you can compute this resultant. But we can do better. So here's a nice thing about the resultant. If f factors into linear terms as x minus alpha I, then this determinant, you can write it as the product of the evaluations g at alpha I. And why should this tell you if the GCD is 1 or not? Well, you're really testing, do f and g have a common root? Right? If g and f share a common root, one of the terms in this product is 0. And otherwise it'll be non-zero. Right? So this should convince you that this is telling you something about whether G and F are co-prime or not, and it happens to be the determinant of this matrix. So as a corollary of what I just showed you, we get that the resultant can be computed in AC0. And actually, this also gives you something nice. It tells you that you can compute the discriminant of a polynomial in AC0. And what's the discriminant? This is just the resultant of a polynomial and its partial derivative. I guess if there's one variable, this is just the derivative. And why is this discriminant interesting? Well, the discriminant is 0 exactly when f has a double root. And in fact, you've seen one of these before. If you look at the discriminant of a quadratic polynomial, then you'll recognize this. It's exactly b squared minus 4ac, right? This tells you if a quadratic has a double root, and there's some generalization to higher degree. So in constant depth, we can test if two polynomials share a root. And in fact, we can also, as an immediate corollary, check if a polynomial has a double root. And this was not known. Prior to this, the best we knew about the resultant was NC2. This is really some, now we're starting to cook with some gas. So any questions on this?
So what is the depth? Hard to know.
Something maybe around 10, 11. It's not too big.
Are there any lower bounds? Like
That's-
not in 2?
Yeah, it's certainly not in 2 because that's just counting the number of monomials. But I actually don't know what the right depth is. And I guess in principle, this is a question you could try to answer because we have tools for lower bounds at constant depth. But I don't know what the right answer is. Okay. So now we're starting to do something related to the GCD. Let's see how we can make even more progress towards that. So I want to look at a special case of the GCD for what are called square-free polynomials. And I don't want to define these precisely, but these are just polynomials without a repeated factor. If they have a factor, it only appears with multiplicity 1. And it turns out if you pick a polynomial at random, it's almost always square-free. So this, you should think of this as not too restrictive an assumption, but we'll need to fix this up later. Okay. So here I have two polynomials. Here, all the alphas, betas, and gammas, these are distinct elements of my field. Right? There are n plus m plus d distinct numbers here. None of them are secretly equal. What we want, well, we want the GCD, right? Which we know is going to be the product of the x minus gamma x. So how are we going to do this? Well, let me show you a trick. So I'm going to add a new variable z, and I want to look at the following polynomial. It's z minus x times g. And what I'm going to do is I'm going to evaluate this over the roots of f, where I'm putting the roots of f into x. And I'm going to do some tricks with this. But let's just look at what are the evaluations here. Okay, so at alpha 1, this is, z minus alpha 1 times g alpha 1, which this is some non-zero polynomial, right? This is not zero. Alphas, these aren't roots of g, so this is some non-zero number. And same for all the evaluations at the alphas. These are all not zero. But what happens when you start evaluating at the other roots of f, which are these gammas? What do you get? Well, you have z minus gamma 1, that's not zero, but then you have g of gamma 1. And this is zero because the gammas are shared roots. And the same thing happens for all of these. So, these are some numbers we can play around. We can compute some functions of these. We can maybe add them, multiply them. We can do other things. How could we possibly hope to get Well, let's see what we can do. So the only thing we really know how to do at this point is to take the elementary symmetric polynomials and evaluate them at these lambdas. This is really the only thing we know how to do right now. So let's do that. So say I take the degree k symmetric polynomial. Well, what is this? Well, I'm going to break up the index of the sum into two sets. So I have some collection of the first n lambdas, and I have some collection of the remaining d. I pick a total of k of them. So S tells me which of the first n am I picking, and T tells me which of the subsequent d am I picking. All right, I'm just expanding the definition and writing the notation a little bit more nicely. But now, the last d of these lambdas, they're all zero. So if this set T is non-empty, I get a zero term. So in fact, this is only summing over subsets of n of size k of the product of these lambda i's, right, which is just the same thing as the elementary symmetric polynomial evaluated on the first n of these lambdas. Okay, why is this useful? Well, what's the elementary symmetric polynomial of degree n? It's the product. Right? This is the product. And if you expand this out, well, what do you get? You get the product over I of z minus alpha I times g of alpha I. And up to this scaling, this is the GCD. So what's the, so what's the algorithm here?
Maybe we should select that we don't know n.
Yeah. So in the analysis, we don't know n. So somehow we'll need to find n.
Not the GCD. This is like f divided by the GCD, right?
Sorry, no, this is f divided by the g. So we'll divide f by this. Yes, sorry. The point is, we've somehow figured out which roots belong to the GCD and which ones don't. Right? Somehow we've separated the alphas and the gammas. That's the take. Okay. Let me just tell you the algorithm. So as I said, we don't actually know this value of n, right? This is hidden to us. We know it for the analysis, but in the algorithm, we don't see this. So what we're going to do, well, we're just going to compute these elementary symmetric polynomials for all k between 1 and n plus d. We know n plus d. This is just the degree of n. That is known to us. And now we can actually compute the value of n. This is the maximum value of k for which this ek is not 0, right? Because if I take degree n plus d, I'll get 0. If I take degree n plus d minus 1, I get 0. And only at degree n do I see something non-zero. And n is just the largest degree where I see something non-zero. Now, one point maybe I should just admit to is this is an operation that, this model of algebraic circuits just doesn't implement. This is not actually, this is not a polynomial function. But if you're implementing this on, say, a computer, you have these numbers in front of you. You can just look at them and compute this quantity in parallel. So you're still genuinely getting a parallel algorithm. It's not exactly a circuit, but each one of these is computed by a small circuit. So what we'll end up getting is we'll compute the GCD, and we'll output a small list of circuits. All of these circuits are constant depth. One computes the GCD, and you have to do some kind of test to figure out which one is the correct one. Never mind. Okay, so now we can do here, so normalize this En of lambda to have a leading coefficient 1.
So you have lambda is a polynomial in C.
Yes, yes. So this is some polynomial in Z. And we're going to output f of z divided by this En of lambda. Right? As Johan pointed out, this is actually the part of f that's not in the GCD. So I want to divide this out. This will give you back just the product of the gammas, which is precisely the GCD. So any questions on this? Okay. Great. So this gives us the GCD for square-free polynomials. And now we need to work a little bit harder just to extend this to the GCD for arbitrary polynomials. So how are we going to do this? We'll actually just reduce to the square-free case. So for this, I just need one notion, which is something called the square-free decomposition of a polynomial. So this is some sequence of polynomials. Let's say that this is the square-free composition of f if three conditions hold. The first is that each fi is a square-free polynomial. The second is that f is the product of fi raised to the odd. And the third is that these fi's should be pairwise co-prime. So what is this trying to capture? Fi is capturing the factors of f that appear with multiplicity I. Maybe just as an example, if I have a polynomial like x1 to the 3, x minus 2, x minus 3, then what would the square free decomposition of this polynomial be? Well, there are two factors that appear with multiplicity 1. No factors that appear with multiplicity 2, and there's one factor that appears with multiplicity. Right? So this is something like a partial factorization of f. And what we're going to do is we're going to reduce to the square free case by computing this decomposition. If we can do that, then we'll be able to do something with the GCD. Actually. So here's what we have. So given polynomial f, we can compute the square free decomposition in AC0. And what does this look like? Well, I won't tell you the whole algorithm, but let me sketch why this should be true. So let's write f as its factorization. So here, the factor x minus alpha I has some multiplicity ai. This is some natural number. And here's what I'm going to do. For a natural number r, I want to look at a polynomial now in 3 variables, x, z, and w. And I'm going to try and do a similar trick to what we did in the square free case. I want to define a polynomial that is going to suppress roots of f of high multiplicity and allow low multiplicity roots to come through. Right? What we did earlier was really we took f and we suppressed the roots that it had in common with g. Right? Now we're going to do this multiplicity into account. So what is this? So I'm going to try and pick up a factor of z minus x, but when do I want to suppress this? Well, here what I want to do is I want to get the roots of multiplicity less than r. So how do I get that? Well, first, I want to ensure that whatever number I'm putting in for x is genuinely a root. Next, I want to ensure that the partial derivative of f at that number is also 0, right? This is saying it's a root of multiplicity of these two. And then you keep doing this, and you ask that all partial derivatives up to order r would vanish. Now this is great if I could somehow, force each of these to but if I were somehow able to force an independence between these, right? If I could say that, I suppress this factor of z minus x exactly when this is 0 and this is 0 and this is 0, right? If I could do that, that would be great. But, the issue here is, well, there could be some cancellations or some other thing happening, right? I could suppress factors I don't want to suppress. So we add some extra coefficients, some powers of w, right? Now, the only, if I evaluate at some alpha I, how would this factor be 0 exactly when all the f's are 0?
As a polynomial in W.
As a polynomial in W, yes. And the point is that this will suppress high multiplicity factors of f. So this, same trick using the elementary symmetric polynomials allows us to compute this product. So I look at the product of factors that have multiplicity less than 1. But I still pick them up with the same multiplicity. So now we're almost done. If you look at the rth part of the square free decomposition, right? I want the factors that appear with multiplicity exactly r. Well, what is this? This is a quotient. This is the factors with multiplicity at most r divided by the factors of multiplicity less than r. I can compute the top and bottom, constant depth. And we saw how to take quotients earlier. So now we get this. I almost have the square free decomposition, but there's this power of r sitting around. So how do you get rid of that? Well, you take this rth root by dividing the power sums by r, right? These power sums are playing the role of a logarithm, right? And so if I divide a logarithm by r, that's the same thing as taking an rth root. So this gives us the square free decomposition. Okay. And so we're basically done. Now we can compute the GCD. In constant depth. So I guess before I show you this, any questions about this square free decomposition? Okay. How do we do this? So let's factor f and g. Here are these ri's. This is the union of the roots of f and roots of g. That is to say that some of these multiplicities, ai and bi, they could be 0, right? Okay. The other thing I need is I need the square free decompositions of f and g. So I'll write f as the product of fi to the I and g as the product of gi to the I. We saw we can compute this in constant depth. So how does the GCD come out of this? Well, let me write down what the GCD is. I'll manipulate the expression a little bit, and then we'll see that it's actually something we can compute. What is the GCD? Well, it's the product over to these factors. And what's the multiplicity here? Well, it's the minimum of AK and BK, right? That's the GCD. So now I want to break up this product by stratifying over the values of the AKs and the BKs. So here I have some product over I and J. And I want to take the product over factors where AK is I, BK is J, right? So I'm looking at factors that appear with multiplicity I in F and J in G. And this is X minus. Okay. And now I know the values of AK and DK. They're just I and J. Okay. And now, what is this? Well, these are the roots that appear with multiplicity I in F and with multiplicity J in G. Think about this, really. What is this? Well, this is the GCD of Fi and Gj, now raised to the power of min ij. So Fi and Gj, these are square free. So I can compute this GCD. We saw how to do this earlier. So now you just write down this product. And this gives you the GCD with any multiplicities on the roots of F and G. Yeah, so any other questions about this?
Is about this comment you made earlier about the max. So is GCD computed by a single like circuit?
No, so what's going on here is let's go back just to the first case. Well, what did we do? We looked at we had this polynomial b, which was z minus x, and we looked at E1 of h at the roots of f, 2 n plus b. Where here I have n roots that aren't in common with g and d roots that are, right? And we saw that I have a bunch of zeros in the high degree elementary symmetrics, and at some point I see one that's not zero, right? And that's the one that tells me what are the roots of f that are not in common with g, right? So if you actually had numbers, if you had the coefficients of f and g, you could compute all of these in parallel and search where do you stop seeing zeros, right? Where do you see something non-zero? You have to select that one. Formally, algebraic circuits, they don't implement this instruction. But something like this is necessary. Let me just show you maybe one example why. If you think about the GCD just of 2 degree 1 polynomials, this is a very discontinuous function, right? This is 1 if alpha and beta are different, and this is x minus alpha if alpha and beta are the same. So the GCD itself is very discontinuous, but algebraic circuits, formally speaking, they compute continuous functions. So there's going to be some kind of fudging that I have to do here. Does that answer your question? Okay, great. Yeah.
I have a question, not about what you said, but suppose I want to compute the GCD of, I don't know, k polynomials. Is there also a way to do this in AC0?
Yes, there is. Yes.
I couldn't hear the question.
So the question was, this is GCD of 2 polynomials, GCD of n polynomials. Is that in AC0? And the answer is yes. Also for the LCM, you can do this in AC0. The proof for many polynomials, you need to do something different here, right? Because if I have n polynomials and I take all different ways of pairing up the square free decompositions, I pay like a factor of n to the n.
Yeah.
So you need to do something else. And I can tell you about that in a little bit if you'd like. Did you have a comment, Toby? Okay. So maybe before moving to I want to ask a question. Which is, the GCD, it's really like taking the minimum of the multiplicities of the roots. Right, so if I have F and G, then the GCD, well, this is, you take all of the factors, you take the minimum of their multiplicities. What other functions of the multiplicities can you put here? Right? The LCM would be something like the maximum. The product would be taking sums, right? So you could have F times G. This is X minus I to the AI plus BI. Right? You can certainly add these. What else can you do? So here's a question. Say I want to implement some really weird function. I want to compute the product now where I multiply these multiplicities, right? So the root Ri now has multiplicity AI times Bi. Could you do this in constant depth? Does anyone see it?
Could we do it at all?
Yeah, could you even do this at all? What does this even mean to multiply the multiplicities? I'm not really sure I have a great answer for that.
Like you had the minimum of I and J over there,
Yeah,
which is something that's hard coded into your circuit, right?
yeah,
For what? I mean, what, instead of this, couldn't you just put like a product of I and J?
exactly. So you could have just put I times J. Right? I could put anything I want there. So in fact, you get something which, like, it's not even clear that it should be computable in an algebraic way, right? So we get something very nice, for any function, say E, that takes a pair of natural numbers and gives you back a natural number. We can apply P to these exponents, right? We can do this in AC0, because as Yotam pointed out, you just modify the proof in this one spot. And in this, I feel like this is very strange. Why can you do this?
Why can you do this, and also can you find an application for?
Yeah, if you could tell us why this is interesting.
And we can do it for 2, 3, 4, 5.
Yeah,
Any constant. Some interesting function you can.
yeah,
The
so,
minimum, maximum, you can do the median.
yeah, so sorry, go ahead.
No, I wonder if it has any significance.
Yeah, so, this proof, if I had, 5 polynomials, it's clear that this gives, you're gonna pay like a 5th power in the exponent of the circuit size, but you can still get a polynomial size constant depth circuit for GCD of 5 polynomials. And you could take, arbitrary functions of, 5 multiplicities, like the median. What does the median multiplicity mean? Is there an application of this? Yeah, this is pretty cool. So maybe the last thing I'll say is to address Yotam's question about, what do we do if we have n polynomials? How might you compute their GCD? GCD of say n polynomials. So say I have n polynomials. So this is not the square-free decomposition anymore. These are distinct polynomials. Right, if I take these, if I were to take the square-free decompositions of all of these and then take all possible n tuples, I would pay far too much. What can we do instead? So the first thing I want is I want to compute the square-free part of their product. Right, and how do I do this? Well, I take the product, now that's one polynomial, and I know how to take the square-free part of one polynomial. Okay. So, what do I want to say? So again, I'm going to try and suppress roots of this polynomial that appear with large multiplicity in all the f's. So we're going to do a similar trick that we saw before. So I'll have z minus x, and then here, I'll have f1 plus w times the first derivative of f1, the r minus 1 rth derivative of f1. And now I just take higher powers of w and I throw in the derivatives of all the other polynomials as well. Okay, is it clear what I'm saying here? So you have something like n times r terms that are appearing here. And what happens as you evaluate this over the roots of the square-free part? Right? When will this z minus x term be suppressed? Well, it'll be suppressed if every one of these polynomials in x vanishes. Right? So when is it suppressed? It's suppressed when I have a high multiplicity root of f1, a high multiplicity root of f2.
The same root.
Yeah, the same root, right? It's the same root. It has to have high multiplicity in f1, f2, f3, and so on. Right? So this same trick what you get is you get the product over the roots where and let me see, what is the right thing here? So you either have that, so when does this term survive? It survives when I have a root which is low multiplicity and at least one polynomial. So this is saying that either in the first polynomial I have multiplicity less than r, or in the second polynomial I have multiplicity less than r. And so on, right? This will give me roots which are low multiplicity in at least one of these polynomials. And if you divide the square-free part by this guy here, what this is really doing, this is negating this condition on the multiplicities. Right, so what you get is now you get a product where you have all the roots of multiplicity. Sorry, you have roots that appear in each polynomial with multiplicity r. And let me call this s subscript greater than or equal to r. This is capturing, these are the roots that appear with multiplicity at least r in each of f1, f2, f3, and so on. Why is this useful? Well, I can just write it here. If you look at the GCD, This is the product over, say R goes from 1 to n of how many times do I pick up a root? Well, if the root has multiplicity, say 5, I pick it up in the first 5 terms, each with multiplicity 1. So this will give you the GCD. Right? You have to compute these, these polynomials here, which again is using the same trick that we're using again and again of somehow filtering out roots by comparing polynomials. But we're doing this all without factoring the polynomials.
So you're saying that you have to sort of bend the notion of arithmetic circuits in order to do this.
Mm-hmm.
Is it any different than just saying, if you're working over the rationals, you can do it all in uniform TC0?
Probably this is the same thing.
But in all the, essentially all the papers in arithmetic or algebraic complexity, where you want to cater to non-continuous functions, so determinants is fine, it's a polynomial. When you do GCD and all these old papers of Borodi and Together, and in all these papers, the model they usually specify is you have a normal arithmetic circuit and a test for 0, which you can branch on, which of course is implemented in CC0, implemented by Piram, yeah. So when you have to, there's no way around it, you do this, and that's the only thing you need. So you can adopt the notion of arithmetic circuit with several outputs, one of which is good, or you can test. It's all natural. Yeah. So that's true with whether it's CC0 or NC2 or all of them, yeah.
Can you also compute the polynomials in Bezout's identity?
Yes, we can. So we can also compute, for a constant number of polynomials, we can compute the Bezout coefficients. And this matrix I showed you earlier that has the coefficients of f and g in these parallelograms, the Bezout coefficients really are like inverting that matrix. We can also invert that in constant. And if you're interested, I can tell you how to do this later. More questions? This is all I had to say. So I'm done.
Thanks.
Yeah.
More questions.
Did you think whether there is any meaning? You mentioned other functions that you can take, right? Instead of the minimum j before. Is there any meaning of a determinant hiding in one of these other functions?
I don't think so. Because we can compute these, at least for constant number of polynomials, we can compute all of this in AC0.
Yeah.
And we know the determinant isn't in AC0.
Right, I meant a specific structured matrix where this corresponds to.
I'm not sure I understand.
The resultant is a determinant, which we can compute. So it's a determinant of some structured matrix.
Yeah.
So what's the question whether other structured?
Yeah, whether other structured matrix correspond to other things that you can put in the exponent instead of the minimum.
That I don't know. Yeah. Yeah, that's a good question.
I mean, the minimum is not the
the
resultant,
point plot. So what would it be? You just multiply to polynomial, so you get a plot.
Yeah.
You want to express it as a determinant, you can by variant completeness result in general, but you probably want to do it with a structured one.
Yeah.
I don't know.
Sorry, I'm a little confused. I thought the pump function P was only for when there's high multiplicities.
Sorry. This?
Yeah.
So I'm sorry, I'm not sure.
No, sorry. It was in response. I thought that was functions of the multiplicities of the roots, right?
Yes.
The resultant is only defined when it's free. Otherwise, the resultant of stuff. Oh, wait, no, that's not true.
No, the result.
Because it's two different polynomials. Okay.
Yeah.
the discriminant is, right, the discriminant
yeah,
of
yeah.
one polynomial is exactly one it's square of it.
Yeah.
I have a question.
Okay.
What is the simplest program that you think is not an ACD? Simplest polynomial.
What do you mean the simplest?
Polynomial you want to compute, but it's probably not. Determinant is an answer, but maybe there are simpler polynomials.
Do you want something that's conjectured, not?
Yeah. What
Uh,
would you challenge someone to prove an zero log for that's really much simpler than determinant? So
that's a good question. I don't know.
yeah, I don't know. I mean, there is one we tried and we don't know how to do, but it's the determinant of a top list matrix.
But that we know is not an AC0, right?
We think it's not an AC.
No, we have a proof. It projects the continuant in the border sense, right?
Yeah, but we don't know that it's not an AC.
No, the continuant captures.
But the continuant, they can prove Newton and our friends can prove a law bound for the continuant.
They have a, yeah, so you
Ah,
need
yeah, they have a
depth hierarchy. So if the continuant was in constant depth, say the continuant's in depth 100. Take something that's in depth, 200, but not in depth 100. Reduce it to the continuant because it has a polynomial sized formula. Now implement the continuant in depth 100 and you have a contradiction.
Yes, so you probably should have mentioned it as a law bound they prove. So not only is the determinant not in AC0, but actually the determinant of top list matrix
Yeah,
is not in AC0. That's
Yeah.
a stronger law bound.
right. Yeah, I mean, yeah,
It's top list matrix.
It's diagonal.
yeah. So it's
Oh, and the matrix.
But the other way around, okay, yeah.
Yeah, it does.
something like,
You want the determinant, then write the house.
I guess it doesn't matter for the.
Determinant, you replace all the columns.
yeah, this is a. This is a Toport's matrix, right? It's constant on the diagonals and you want its determinant. You can prove that this is not an AC0. It's totally unclear if this thing is in NC1 or if it's complete for NC2. This is some intermediate thing that, we know it's not here. We know it's in here. Don't know if it's here. So yeah, we don't know if it's here. We know it's at least in here. So it's somewhere in between.
So actually, it's a good question. We don't have a candidate that maybe still in AC0, but we cannot do it.
Yeah.
What's the intuition for determinant not being an NC1? Is it just kind of like,
Okay. So let me tell you a second algorithm for the determinant. Okay. So I have a matrix A and it has a set of eigenvalues, right? The determinant is the product of the eigenvalues. And if I look at the trace of a power, well, this is a power sub in the eigenvalue, right? So if I can compute all these traces of powers, I use Newton's identity and I get the determinant. Okay? So the question is, how hard is it to compute the trace of an nth power of the matrix? So it's really a question about matrix power. How much depth do you need to compute the nth power of an n by n matrix? And the obvious answer is, well, you do a binary, you compute the matrix power in some binary tree. Right? The binary tree will have log depth. Each matrix product costs log depth. And not clear that you should be able to do better than that. So if you could even take powers of a matrix faster, you get the determinant.
questions.
Hey, Robert, can you hear me?
Yeah, hi, Victor.
Hi. So this was all for the complex numbers, right? I'm
Yeah,
wondering if you're working in a prime field where you don't necessarily split the polynomials, can you still take GCDs in AC0?
yeah. So as long as your field is large size and large characteristic, the algorithms work. It just helps with the analysis to say that, my polynomial is split into linear factors. It's really happening in the analysis.
I see. Okay, thanks.
Mhm.
So how large? So like if you're working over fields of polynomial size?
Yeah.
Yeah, that's good enough.
Bigger than the degree, basically, or a little bit, well,
Yeah, maybe bigger than the sum, of the degrees of the polynomials whose GCD you want, but probably not much bigger than that.
I thought in the exponential that you wrote in identity, isn't it like I factorial in the denominator?
No, there was I in the denominator.
Even I factorial is okay. Like, because you only care about primes.
I see.
Yeah.
all right, thanks.
Right, thank you.